In this lesson, we are going to look at the imaginary number I as well as complex numbers. So first, let's introduce I. You've probably seen this before, but I just want to remind you what it is. Suppose we have the quadratic equation x squared plus 1 equals 0, or in other words, x squared equals negative 1. There is no real number whose square is negative. So what we do is we define an imaginary number. So we say imagine that there is a number whose square is negative 1. We call it I, and it's the square root of negative 1. So that the solutions to this quadratic equation are I and negative I. So there are two solutions. One is I, the other is negative I. So that if you're I and you plug this in for x, I squared is negative 1. Negative I, when squared, also returns you negative 1. So those are the two solutions to this quadratic equation. So I is the number whose square is negative 1, but what's interesting is that when you start raising I to other powers, you notice a pattern. So let's run through some powers of I. So first, let's look at I to the 0. In the usual way, we say I to the 0 is 1. Then I to the 1 is just I itself. And then the whole reason we introduce I is so that we can say I squared is negative 1, which means that I cubed is going to be I squared times I. So that's going to be negative 1 times I, or in other words, it's negative I. Let me keep going over here. What is I to the 4th? A couple ways you could think of this. It's I squared squared. Let me write that down. I squared is negative 1. That's the whole reason we introduced it. You square that and you get back positive 1, which means that I to the 5th is I to the 4th times I. So that's just going to return you 1 times I. So I to the 5th is I. I to the 6th would then be negative 1. So that I to the 7th is negative I. If you compare these two columns, you'll notice that both go 1I, negative 1, negative I. You can imagine if I wrote I to the 8th, 9th, 10th, and 11th, we would see 1I, negative 1, and I. So that's one neat thing about I is you have this repetitive sequence of 4 possibilities when you raise I to an integer power. The number I we just met is a pure imaginary number. Other pure imaginary numbers would be negative I, 7I, negative 15I, multiples of I like that. Of course, we also have real numbers like negative 4, 0, pi, e. And when we take the two and we combine them, we get complex numbers. So we often write these as z equals a real component plus I times an imaginary component. And let me show you how you might land on one of these numbers. So consider the quadratic equation z squared minus 2z plus 10 equals 0. Let's try to solve this with the quadratic equation. We'll say that z, sorry if you can't read that, trying to make it a little bolder. Okay, z is negative 2, so 2 plus or minus the square root of 2 squared, so 4, minus 4 times 1 times 10 is 40, all over 2 times 1. Okay, our discriminant here inside of the square root is negative. Let's simplify that to negative 36 so that we can say that the solutions to this quadratic equation look like 2 plus or minus the square root of negative 36 divided by 2. This negative 36 we can think of as negative 1 times 36. The square root of a product is the product of the square roots. So this is going to be I times 6. So overall, the square root of negative 36 is 6I. And then this simplifies into 1 plus or minus 3I. So that means that for this quadratic equation, we have two roots. One of them, which I'll call z1, is 1 plus 3I. This is a complex number whose real component is 1. So this is the real component of z, which is 1. I don't think that this marker can be seen. Let me write that again, but how about with a different color? Okay, trying this again. The real component of z1 is 1. So that's what I'm calling A in the notation up above. Whereas the imaginary component is the 3. So I'll say the imaginary component of Z1 is 3. So that Z1 is 1 plus 3i. The other solution is Z2, which is 1 minus 3i. And if you compare these two, you'll notice that they have the same real component. So the real component of Z2 is also 1. The imaginary component, however, differs by a sign. So this one has an imaginary component of -3. When a pair of complex numbers satisfies the property that they have the same real component, but they have the imaginary components differing by a sign, we call them complex conjugates. So Z2 is the complex conjugate of Z1, which we can denote with a bar symbol. So we could also say that Z1 is the complex conjugate of Z2. I don't want to go too off topic, but what you would find is any quadratic equation that has complex roots will have their complex roots looking like this. So their complex roots would be complex conjugates. Let's do some arithmetic on complex numbers. Suppose z is a plus ib and w is u plus iv. So the real part of z is a, the real part of w is u, whereas their imaginary components are b and v. We are going to add them together, multiply them together. I'd also like to show you how to divide by a complex number. The theme is always to try to take the result and write it as the real component plus I times the imaginary component. So for addition, we would like to add z and w. So that's a plus ib plus u plus iv. Rather than have these four terms, let's combine like terms. And with complex numbers, like terms means real part with real part, imaginary part with imaginary part. So the real part of their sum is a plus u, and then the imaginary part is b plus v. It's the imaginary component of the sum of z and w. Likewise, we can multiply them. So we'll do a plus ib times u plus iv. We distribute in the usual way, and then when we take our result, we'd like to group it into real and imaginary components. So this is going to be au plus, I'll write iAV plus IBU. And then let me first write plus I squared BV. Here, however, I squared is -1. So actually this fourth term here is a real number. So if I group these real with real, imaginary with imaginary, I'm going to say the real part is AU minus BV. And then the imaginary part is AV plus BU. Okay, let you take a moment to look at this, and then we will take z and do its reciprocal. Essentially, we'll divide 1 by the complex number z. Okay, to take a number and divide it by a complex number is, well, in this case, to write 1 divided by a plus ib. The thing is, I would like to take this result and break it into a real part plus I times an imaginary part, just like we did for these first two computations. I can't break up a denominator. So what I need to do is take this fraction, here's the technique, multiply the numerator and denominator both by the complex conjugate so that you're not actually changing anything. So in this case, I'll write a minus ib divided by a minus ib like that. Now across the numerator, we get a minus ib. When I multiply this denominator by its complex conjugate, watch what happens. We'll have a squared. Then we will have minus iab plus iab. So those are actually going to cancel. I'll write them out and then we'll cancel them. And then we will have minus I squared b squared. So let's just look at this denominator for a second. This cancels with that, so the middle two terms cancel. That leaves us with no imaginary component left in the denominator because negative I squared is going to be -1. So overall, this entire coefficient right here, the negative I squared, is going to become +1. So that our denominator is actually a squared plus b squared. We can now take the numerator and split it up so that we'll have a divided by a squared plus b squared. That's going to be the real component. Minus I b divided by a squared plus b squared. So like this, we've taken 1 over z and written it as a real component plus an imaginary component. The theme of the computations we just did is that complex numbers have a real part and an imaginary part. And that means that you can think of them really as having two independent pieces, kind of like having an x coordinate and a y coordinate. And that's exactly how we visualize them. So complex numbers we plot on a plane where we say that the horizontal axis is the real component and the vertical axis is the imaginary component. What that means is that if you wanted to plot a real number, you would plot it on this horizontal axis. If, on the other hand, you wanted to plot an imaginary number, you would plot it on the vertical axis. Complex numbers would get plotted in the 4 quadrants. So, for example, let's say that this is the real component A, and then this, let's say, is BI or IB, so that my complex number A plus BI can be thought of as this number right here. So it has a real coordinate of A and an imaginary component that looks like IB. The complex conjugate would be the reflection of this number over the real axis. So it has the same real component, and then let me put about negative IB down here, so that the complex conjugate of Z would live down here. Let's do some arithmetic with Z and Z conjugate. So first, let's add them together. What is Z plus Z bar? Well, that's going to be A plus IB plus A minus IB. Let me write that down. A plus IB plus A minus IB. The imaginary parts cancel and we're left with 2A. That's twice their real component. So one thing you could say from this is that the real component of Z is Z plus Z bar divided by 2. What happens if you subtract Z bar from Z? So do Z minus Z conjugate. I'll give you a second to work that out on your own. Okay, let's see if you got a way to write down the imaginary component of Z. If we do Z minus Z bar, we get a different type of cancellation. So that's going to look like A plus IB minus A minus IB. The A's cancel, we get a total of I times 2B. We can solve for the imaginary component B now to say that the imaginary part of Z, which here I'm specifically referring to that coordinate B, is Z minus Z bar divided by 2I. You could try to make this denominator real if you wanted to, but I think I'll leave it there. So Z minus Z bar divided by 2I returns you the coordinate B. There's one more operation I want to do with Z and Z bar here and visualize on this complex plane, and that is multiply them together. So what is Z times its complex conjugate? We actually just did this when we did the division of 1 divided by Z. So we know from the previous slide that Z times Z bar is going to be A squared plus B squared. That's this coordinate squared plus this coordinate squared. That's the square of this hypotenuse, if you will, right here. So if I took the square root, I would get the distance from Z to the origin. That's what we call the modulus. Looks like absolute value of Z. It is the square root of Z times its complex conjugate. Or in other words, it's the square root of A squared plus B squared. And to place it on this picture, the modulus of Z indicates the length of this line segment I just sketched. Okay, so that is just a quick look at the complex plane and how to visualize complex numbers on this plane.